Hello, my name is Christian Murphy, and I am presenting my work on appearance-controlled face texture generation for video game characters. In current game production environments, 3D morphable models are often used by artists for face mesh editing. However, they still have to create the textures for these meshes by hand since there are no current methods which provide the level of control they need for the texture's appearance. Artists would like to control a texture creation tool by providing some details about the target character. These include the character's face mesh, their skin, hair, eye, and lip color, facial hairstyle, and their age and gender. The textures also need to be at 4K resolution to be able to be used in production. Finally, all of this has to be done using a limited data set of 3D stand individuals, only 126 samples, and 10 of these are removed for the test set. There are a few related works which we wish to highlight. First is Learning Formation of Physically Based Face Attributes by Li et al. In 2020. Their system allows users to generate a mesh and texture from age, gender, and race variables. While they obtain high-quality results, their controls are not precise enough for production environments. Second is High-Fidelity Facial Reflectance and Geometry Inference from an Unconstrained Image by Yamaguchi et al. In 2018. They use image-to-image translation methods to fill in unknown areas of textures inferred from a photo. Parts of our network architecture come from this work, which was designed specifically for face textures. Our solution uses image-to-image translation as the generation method. To be able to use this method properly, input and output image pairs are linked by having meaningful data in the same locations. This is normally used for image segmentation or segmentation to image generation. Therefore, the first step we must do is convert all of our input conditions into the same image format. We choose to use the base mesh's UV mapping as the base format for the input images, since this is the format of our target textures. We start by converting our mesh database into state maps, a method by Gesser et al. In 2019. The process starts by per vertex normalization of the mesh dataset that all of the meshes are scaled between 0 and 1. Next, each vertex has their XYZ values placed in image space using its UV coordinate. Once all vertex values have been placed, the triangles are then filled using barycentric coordinates. Next input, which is converted into UV format, are the appearance controls. To put a few chosen colors into a large image, we first create a generic segmentation map that covers all of the main locations for each appearance control to be used for the entire dataset. These include regions for the skin, hair, lips, eyes, and the mustache, goatee, and jaws and neck facial hair regions. With this segmentation map completed, the pixel from each area in the target texture is used to represent the overall appearance attribute value. For example, a pixel is selected from the forehead to be used as the skin color value. After a value for each region is selected, they're used to fill in each segment in the segmentation map. Call this result the feature map input condition. For the age and gender condition, we use a one-hot encoder to transfer the values into a binary format. Encoding is then repeated until it is the same size as the input images. Now we show how our new input variables compare to the original problem definition. There originally was a mesh, but now it is a shape map. The simple selected colors help create a full image using the value's intended location. Finally, the demographic conditions are now in a binary encoding. In the end, it is still the same target texture as before. With all of the data now encoded in a way which image-to-image translation can use, a network architecture had to be chosen for a specific task. Pix-to-Pix was used as the base architecture, and then modifications from related works with different base architectures have been added to it. The first edition is called Feature Flipping by Yamaguchi et al. In 2019. This method takes the output of every layer in the network, mirrors it, and then concatenates it to the original output. This is used specifically for faces since it can use the inherent symmetry within them. The next edition is by Gesser et al. In 2019, where they create a branch network output, where there are individual layers for each of the types of outputs the network has. We use this because we are also generating displacement maps and possibly more types of maps in the future. Finally, we train with 3 discriminators instead of 1. The two extra discriminators are given half and quarter resolution images so that each one sees more of the given image at once, leading to better global awareness during generation. This method is called multi-scale discrimination and was done by Wang et al. In 2008. Early on in our test results, we saw that the feature map condition was not being matched exactly. We believe this was because the network quickly overfit to the small dataset, so it did not have time to learn the link between the feature map input and the target texture. To try to fix this, we add a chance to modify both of these images in a randomized way. 3 floats between 0 and 1 are uniformly sampled and multiplied by each RGB channel in the input and target images. Because the feature map was created from values in the target texture, we can modify both at the same time instead of creating an all-new feature map from the modified texture. This augmentation works by strengthening the network's understanding of the relationship between the input and output pairs. To be able to use the generated textures in production, they must be at a high resolution, at least 4K. Our initial textures are generated at 1024 by 1024 resolution, so they must be scaled up by 4. Because of our limited dataset, we therefore train a SuperResolution network separately from generation so that we can do some extra augmentation. To make sure that the network does not overfit to our lack of data, we train it with small 64 by 64 resolution randomly selected patches. The patches have a 25% chance to be left-right flipped and a 25% chance to be up-down flipped. There is then a 75% chance to add Gaussian blur to the patch so that it may work better on generated textures. Along with simple image augmentation, we include dataset augmentation by utilizing the Chicago Face database. The photographs in this database are all uniformly taken, front-facing photos. Therefore, we can take patches from these images as well, because front-facing photos and face textures are not so different at small scale, as shown below. Next, we show the performance of our texture generation on our test set. Our test set is comprised of individuals from varying demographic backgrounds, appearances, and facial shapes. As can be seen, there is a high visual similarity of the ground truth and generated textures. We believe that this shows that artists can use our method as a tool to create the character which they envisioned much faster than they would have done by hand. In order to understand the importance of each of our conditions, we do an ablation study of our proposed methods. On the right is the ground truth texture of the test sample we want our network to generate. Starting with training the network only on the face shape and demographic conditions, we see that the results are not very realistic since the appearances are not consistent throughout. By adding the feature map, we start to get textures which are much closer to the target. However, the appearance values do not match exactly for underrepresented groups in our dataset. Using condition augmentation helps alleviate this problem and gives a very close match to the target textures for these 3 test samples which have very different appearances. We then wish to understand how each condition affects our final train network. On the left is the starting feature map and the texture generated from it. On the right is the ending feature map. We linearly interpolate between these 2 images and input them to the network without modifying any other variables. We see that the texture appearance changes only by color, while the shape-based features like the eyes, nose, and mouth stay the same. Doing the same test as before, but by interpolating between 2 meshes, we see how the generated textures change for the face shape. Now we see that the textures are being changed in the opposite way as before. The features depending on face shape, like the eyes, nose, and mouth, are being modified while the appearance colors stay the same. This makes us believe that the conditions are disentangled in how the network operates. Although our test results have pleasant appearances, we do find a few limitations in them. There's a lack of micro details, such as freckles, moles, and acne. We also find that demographic condition changes the end result much less than we would like. We think that the network is inferring this information from the shape of the face already. And we also find that some combinations of face shape and feature map values can lead to artifacts in the generated texture, as shown below. Based on these limitations, we've come up with a few possibilities for future work on these problems. More advanced dataset augmentation could be done to make the demographic inputs be used much better. This could be done by training 2 networks to change male textures to female and vice versa using CycleGAN by Isola et al. in 2017. The feature map could have micro-detail conditions included by detecting them in the target texture and putting them into the input as well. Finally, we would like to extend our work to other types of objects, such as character bodies and clothing. To conclude this presentation, I would like to list a few of our contributions. Our work is the first to give artists such detailed control over the appearance of generated textures. By using condition augmentation, we are able to obtain good results from a limited dataset size. And using these contributions with a network architecture designed for face texture generation, our system is able to reliably generate a variety of realistic, high-resolution textures. I appreciate your time, and I hope that you enjoy the presentation.